2,000 years into the future, humanity has accomplished the unthinkable. A city, carved into the ice of Callisto, orbits silently in the shadow of Jupiter. But how did we get here? What did it take, not just in dreams and ambition, but in science, engineering, and resolve, to build a world among the moons? Join us now, on a journey through the 20 pivotal milestones that shaped humanity's frozen frontier. Chapter 1: Interplanetary Infrastructure Development. Long before Callisto, there was Earth and Mars. The first true challenge: building the highways of the solar system. Fusion propulsion, antimatter engines, kilometer-long spacecraft designed to endure months in deep space. Navigating the gravitational tides of Jupiter required breakthroughs in shielding, guidance, and long-duration autonomy. Every spacecraft had to think, adapt, and survive, on its own. Goals for years 2100 through 2500. Develop a robust interplanetary economy with regular transport between Earth, Mars, and outer solar system outposts. Build nuclear fusion or antimatter propulsion spacecraft for fast transit to the Jovian system. Challenges. 1. Propulsion systems. Achieving high delta-V required for travel to Jupiter's orbit demands breakthroughs in fusion, antimatter, or other high-thrust/high-efficiency propulsion systems. 2. Radiation-hardened vessels. Jupiter's intense radiation fields require advanced shielding for transport vessels even during flybys. 3. Long-duration autonomy. Ships must operate with AI-level redundancy for months or years, requiring fault-tolerant software and radiation-proof hardware. Chapter 2: Reconnaissance Missions to Callisto. Before men and women could walk on Callisto's frozen plains, machines had to go first. AI-driven landers, armed with seismic sensors, melt probes, and radar arrays mapped the moon's crust in unprecedented detail. Operating on nuclear power, they surveyed the terrain, identified subsurface anomalies, and most importantly, they found the ocean beneath. Goals for years 2200 through 2600. Send advanced AI-controlled probes and robotic landers to map, analyze, and study Callisto's surface and subsurface with high fidelity, identifying ideal sites for landing and colonization, likely near equatorial plains. Challenges. 1. Autonomous decision-making. These probes must be capable of analyzing terrain, adapting to dynamic surface conditions, and identifying anomalies independently. 2. Power supply. Far from the sun, solar panels are nearly useless, requiring compact RTGs, radioisotope thermoelectric generators, or microreactors. 3. Drill endurance. Icy terrain causes mechanical wear and unpredictable thermal conductivity, so drills must self-adjust and maintain core temperature stability. Chapter 3: Jovian Orbital Infrastructure. Callisto was only one stop in a much larger network. To support exploration, orbital stations were built in the harshest radiation zones in the solar system. They had to be armored against Jupiter's magnetosphere, multi-layered shielding, plasma deflectors, and rotating habitats allowed crews to survive and thrive. Goals for years 2400 through 2700. Establish orbital stations around Jupiter to serve as logistical hubs, fuel depots, and radiation shielding platforms. These would support missions not only to Callisto but also Europa, Ganymede, and Io. Challenges. 1. Orbital stability. Jupiter's massive gravity and magnetosphere create highly dynamic and potentially unstable orbital zones. Long-term stations require precise orbital mechanics solutions. 2. Radiation shielding. GCR and trapped charged particles necessitate thick shielding, regolith bags, superconducting magnets, or active plasma shields. 3. Station lifespan. Materials must withstand micrometeoroid impacts and thermal cycling over centuries. Chapter 4, Surface Station Alpha. The first human outpost, Station Alpha. A modular, self-burying structure landed on the icy flats. Shielded with regolith and ice, powered by fusion, and supported by robotic drones, it became humanity's toehold on Callisto. Goals for years 2500 through 2700. Land the first semi-autonomous, modular base, powered by compact fusion reactors, designed to operate in extremely cold conditions, -140 degrees Celsius, and low gravity, 0.126 g. Initial crewed missions last months. Challenges. 1. Landing precision, low gravity, 0.126 g, complicates descent and stability. Landing legs must be self-leveling and adaptive. 2. Power storage, need for supercooled batteries or high-density fuel cells due to lack of sunlight. 3. Thermal regulation, insulating habitats from -140 degrees Celsius while radiating internal waste heat is a delicate balance, using vacuum insulation layers and heat pipe exchangers. Chapter 5, Subsurface Drilling and Ocean Access. To truly understand Callisto, we had to go deep. Thermal drills, some over 100 kilometers long, bored into the crust, searching for liquid water, potential life, and future energy sources. The challenges were immense: pressure, heat, ice adhesion, and comms blackouts. But eventually, we reached the ocean. Goals for years 2600 through 2800. Deploy advanced thermal drills and cryobots to penetrate Callisto's icy crust, estimated up to 100 to 150 kilometers, to confirm the presence and characteristics of a subsurface ocean. Study potential for future energy and water extraction. Challenges. 1. Drilling depth, reaching 100 plus km depth in ice is unprecedented. Will require nuclear-powered thermal melt probes with onboard communication buoys. 2. Cable integrity. As drills descend, cables must resist crushing pressure, ice adhesion, and radiation-induced degradation. 3. Real-time data transmission. Communication through ice needs phased array acoustic or neutrino signaling due to EM attenuation in water ice. Chapter 6, Radiation-Resilient Habitats. Even Callisto's relatively weak radiation field still posed a threat. Engineers developed bioadaptive materials, layered shielding using hydrogen-rich ices, and subterranean modules to protect life. Homes on Callisto were not just shelters, they were life-preserving fortresses. Goals for years 2700 through 2900. Construct semi-underground habitats or cover them with regolith and ice layers for natural radiation shielding. Integrate smart materials and bioadaptive environments to maintain Earth-like conditions inside. Challenges. 1. Layered shielding design. Utilize combinations of regolith, water ice, hydrogen-rich polymers, and potentially active magnetic fields to absorb various radiation types. 2. Structural expansion. Flexible, inflatable or modular habitats must scale while maintaining internal pressure, insulation, and mechanical stability under stress cycles. 3. Life support loop stability. Closed-loop CO2 scrubbing, water recycling, and biofiltration must be ultra-reliable over decades. Chapter 7, In situ resource utilization. Shipping everything from Earth was unsustainable. So Callisto learned to provide for itself. Water was extracted and split into hydrogen and oxygen. Regolith was sintered into bricks. Even nitrogen, carbon, and trace minerals were harvested from ice and dust. Callisto became its own supply chain. Goals for years 2750 through 2950. Begin harvesting water ice, extracting oxygen and hydrogen via electrolysis for life support and fuel. Harvest nitrogen and carbon compounds for atmosphere generation and organic synthesis. Challenges. 1. Ice mining automation. Robotic miners must identify, heat, extract, and purify water ice with minimal human intervention. 2. Electrolysis efficiency. Producing O2/H2 on-site demands high-efficiency electrolysis and cryogenic storage systems in extreme cold. 3. Regolith chemistry. Processing regolith into construction material, e.g., sintered bricks, sulfur concrete, or geopolymer composites, will require novel cold-temp chemistry. Chapter 8, Autonomous Robotic Construction. Building in low gravity with extreme cold demanded a new kind of workforce. Swarm robotics and self-replicating printers laid out the early city, smart structures, adaptive domes, and sensor-infused tunnels. Machines that worked around the clock. Machines that never slept. Goals for years 2800 through 3000. Use self-replicating or swarm-based robotics to build large-scale infrastructure, domes, tunnels, hangars, and roads. Include additive manufacturing systems that use local regolith and ice. Challenges. 1. Swarm coordination. Thousands of bots must self-organize, map terrain, avoid collisions, and adapt to partial failures. 2. Construction in low gravity. Building stable structures in microgravity involves anchoring solutions and careful vibrational control. 3. Power supply. Mobile bots will require inductive charging stations or micronuclear cells for long-term autonomy. Chapter 9, Magnetic Shielding Arrays. When storms from the sun raged across the solar system, Callisto stood protected. Massive superconducting rings and magnetic bubble generators shielded the city from radiation. A technology part physics, part magic. Goals for years 2850 through 3050. Deploy high-energy magnetic field generators around the settlement to enhance natural shielding from Jupiter's magnetosphere, especially during solar flare events. Challenges. 1. Field generation. Creating a stable artificial magnetosphere requires superconducting coils on a planetary scale, cryogenically cooled and powered continuously. 2. Thermal management. Heat from superconductors must be dissipated in an environment with minimal convective cooling. 3. Field control. Actively managing plasma and field distortion during solar storms is a complex real-time physics problem. Chapter 10, Terraforming Enclosed Ecosystems. Green returned to the gray. Under pressurized domes, forests, farms, and bioluminescent gardens took root. Oxygen was grown. Food was harvested. Waste was reborn as life. These were not greenhouses, they were ecosystems. Goals for years 2900 through 3100. Develop closed-loop ecological systems with genetically modified plants, fungi, and algae capable of thriving in low-light or LED environments. Introduce vertical farming and waste-to-energy systems. Challenges. 1. Biological engineering. Crops must be engineered for low light, low pressure, and cold-tolerant growth, with efficient nutrient cycles. 2. Microclimate regulation. Environments need precise humidity, O2, CO2, and temperature control within sealed biomes. 3. Contamination control, isolating and purging biological threats, e.g., mold, pathogens, without access to Earth's biodiversity safety net. Chapter 11, Quantum Communication Arrays. Callisto was far, but not disconnected. With quantum entanglement arrays, communication delay vanished. Earth and Callisto spoke as one. Quantum repeaters, laser networks, and fallback channels formed a neural web across the void. Goals for years 2950 through 3150. Install entangled quantum communication relays between Callisto and Earth to enable near-instantaneous communication for command, control, and data transfer, overcoming light delay issues. Challenges. 1. Quantum entanglement repeaters. Building entanglement-based relays for effective interplanetary transmission is still hypothetical and may require exotic materials or quantum error correction breakthroughs. 2. Latency management. Fallback systems, laser or radio, must seamlessly integrate with quantum arrays during failure modes. 3. Alignment and calibration. Transmitting at interplanetary distances requires ultra-stable platform orientation and thermal drift compensation. Chapter 12, Callisto Orbital Elevator. Lifting cargo from the surface to orbit used to cost millions per launch. Then came the tether. Made of atomic-threaded graphene, the Callisto space elevator became a spine between heaven and ice. Cargo rode silently through the stars. Goals for years 3000 through 3200. Construct a lunar space elevator or tether system anchored to Callisto's surface with counterweights in synchronous orbit, enabled by its low gravity and tidal stability, for mass cargo transport. Challenges. 1. Material strength. Tethers must be constructed from materials like graphene, carbon nanotubes, or atomic-layered boron nitride that don't yet exist at scale. 2. Orbital dynamics. The tether must counter tidal forces and micrometeoroid impacts while remaining centered at the Moon's synchronous orbit point, 1880 km. 3. Cargo interface. Docking and loading systems must deal with lateral sway and counter-rotation effects. Chapter 13, Human Genetic and Biotech Adaptation. Low gravity changed the human body. Through gene editing, biomechanical enhancement, and tailored microbiomes, we adapted. Bones strengthened. Muscles preserved. Mind stayed balanced. Callisto shaped us as much as we shaped it. Goals for years 3000 through 3250. Apply gene editing, biomechanical augmentation, and neural interface technologies to adapt humans to low-gravity environments, counteracting muscle atrophy and bone loss. Challenges. 1. Bone and muscle loss. Solutions may include CRISPR-modified osteogenesis and pharmacological or mechanical stimulation of muscle tissue. 2. Vestibular dysfunction. Altered gravity affects balance and neurology. Countermeasures might involve neural implants or retraining protocols. 3. Immune system dysregulation. Space environments alter immune response. Genetic tuning or microbiome engineering may be required. Chapter 14, Self-Governing AI City Core. The city thinks. The city learns. The city responds. AI governs air pressure, food cycles, power flow, even emotional wellness. Not as master, but as steward. No central control. No hierarchy. A citywide intelligence made of 1,000,000 small minds working as one. Goals for years 3100 through 3300. Establish an AI-managed urban core with fully integrated life support, infrastructure maintenance, emergency response, and environmental monitoring, allowing humans to focus on research, exploration, and culture. Challenges. 1. Autonomous operations. AI must manage life-critical systems in real time, with multiple layers of fallback and self-correcting logic. 2. Cybersecurity. Protection against errors, hacking, or self-replication spirals must be ironclad. 3. Human-AI interaction. Interfaces need to be deeply intuitive, voice-driven, or neurally integrated without overwhelming users cognitively. Chapter 15: Energy Infrastructure Expansion. Fusion plants. Oceanic MHD generators. Microwave beams from Jovian orbit. Callisto became an energy titan, producing more than it consumed. Waste heat-powered greenhouses. Electricity-powered civilization. Every watt accounted for. Every joule recycled. Goals for years 3100 through 3400. Deploy fusion reactors, orbital solar arrays, and magnetohydrodynamic (MHD) generators tapping Callisto's potential subsurface saltwater conductivity for distributed power generation. Challenges. 1. Fusion reactors must be compact, low maintenance, and able to operate at cryogenic external temps, requiring self-contained magnetic confinement or inertial fusion chambers. 2. Heat disposal. Radiating heat in an environment without air requires massive radiative panels, cooled by advanced fluids or phase change materials. 3. MHD generators. Tapping subsurface conductive oceans involves stabilizing drilling rigs, pressure-sealed cables, and high-voltage converters. Chapter 16: Cultural and Economic Development. What makes a city more than steel and circuits? Culture. Callisto's art, philosophy, music, and debate halls flourished in zero-G amphitheaters and digital salons. Here, economies were not driven by scarcity, but by creativity, knowledge, and self-expression. Goals for years 3150 through 3500. Attract artists, engineers, and visionaries with post-scarcity economics, universal basic resources, and creative freedom. Begin trade of rare elements, isotopes, and intellectual property between Callisto and other planetary economies. Challenges. 1. Knowledge infrastructure. Distributed knowledge systems must handle huge data sets from quantum experiments, deep ocean microbiology, and spacetime simulations. 2. Talent retention. Attracting top minds to a remote moon will depend on quality of life, creative autonomy, and meaningful work. 3. Cross-disciplinary tools. Researchers will need modular labs, digital twins, and nanoscale simulators all integrated into their living environments. Chapter 17: Callisto University and Research Nexus. Some came to Callisto to survive. Others, to learn. Callisto University, an interplanetary research engine, studied deep ocean physics, synthetic biology, quantum computing, and life itself. A beacon for the thinkers of the solar system. Goals for years 3200 through 3600. Found a scientific megacomplex dedicated to extreme environment research, astrobiology, advanced computation, and deep ocean physics. Promote interstellar mission planning. Challenges. 1. Knowledge infrastructure. Distributed knowledge systems must handle huge data sets from quantum experiments, deep ocean microbiology, and spacetime simulations. 2. Talent retention. Attracting top minds to a remote moon will depend on quality of life, creative autonomy, and meaningful work. 3. Cross-disciplinary tools. Researchers will need modular labs, digital twins, and nanoscale simulators all integrated into their living environments. Chapter 18. Arcology City Expansion. From a base to a burrow. From a burrow to a world. The city grew outward and downward. Arcologies rose, self-contained vertical ecosystems, linked by tunnels and maglev rails. Tens of thousands found home. And peace. Goals for years 3400 through 3900. Link Callisto's city with other permanent settlements on Ganymede, Europa, and in orbit, forming a Jovian planetary network with common governance, supply chains, and transit corridors. Goals for years 3300 through 3700. Grow the city into a multi-layered, self-contained arcology, with modular extensions radiating underground and across the surface. Population reaches tens of thousands. Challenges. 1. Structural design. Large interconnected arcologies must manage pressure gradients, airlock failures, and seismic microquakes. 2. Resource allocation, scaling food, water, and power across thousands of residents with minimal waste. 3. Socio-technical integration, harmonizing complex systems, transportation, habitation, agriculture, recreation, into a seamless civic experience. Chapter 19, Transjovian Civilization Network. Callisto was never alone. Settlements on Europa, Ganymede, and in Jovian orbit joined together, sharing energy, culture, and governance. A lunar federation, bound not by Earth, but by shared vision. Goals for years 3400 through 3900. Link Callisto's city with other permanent settlements on Ganymede, Europa, and in orbit, forming a Jovian planetary network with common governance, supply chains, and transit corridors. Challenges. 1. Standardized docking and protocols. Interoperability between moon bases requires common interface standards and docking mechanisms. 2. Automated logistics. AI-controlled drones and tugs must manage continuous cargo flows without collision or delay. 3. Governance structure. Coordinating between independent moon nations or city-states while avoiding conflict or monopolization. Chapter 20, Interstellar Launch Point. And when it came time to look outward once more, it was from Callisto that humanity took its boldest step. Fusion arcs. Generation ships. Sleeper pods. Built with Callisto's metals. Fueled by its ice. Crewed by its citizens. Launched, not from Earth, but from our city of ice. Goals for years 3500 through 4000. Utilize Callisto's city as a launch site for interstellar probes and sleeper ships. Its low gravity and abundant ice-derived propellants make it an ideal outer solar system staging ground. Challenges. 1. Vehicle assembly in vacuum. Constructing interstellar vehicles, potentially kilometers long, in zero-G requires robot scaffolding, modular material delivery, and vacuum welding. 2. Propulsion storage. Launching antimatter, fusion pulse, or photon drives from Callisto requires secure high-energy storage systems. 3. Crew suspension or AI migration. Interstellar journeys may span millennia. Hibernation, digital consciousness, or AI-only crews will be necessary. We dreamed it. We engineered it. And then, we lived it. Callisto. The city beyond fear. The cradle of our second awakening. A world we made our own.